Physics students, good afternoon. Mr. Fugit here. What we're going to be looking at today is solving through group problem number 4A, something that we will be doing in class as well. Here in this problem, we're going to be looking at pushing a box across a rough surface. So we'll be looking at drawing a free body diagram, applying Newton's second law, and doing some analysis with Newton's second law to find the desired answer. So I'm going to read a few of the parts of the problem in the background for group problem 4A. Do not forget there is also a copy of your problem on campus, as well as a key located there as well. So our problem statement says this. I have a project that I've been working on for years to catch the lousy roadrunners. This is going to be an acne problem. It says all I need is to get the gear over the road and set it up. The gear is in a box of mass 55 kilograms, so I'm going to be moving a box here. Hey, I'm not a bodybuilder, so I'm not going to push it up there and not carry it. It takes a lot of effort. I push with a force of 230 newtons just to keep our object moving. I barely keep it moving, so it's traveling at a constant velocity that is pretty small. I wonder how rough the box and the ground are, so I want to know the coefficient of friction. So there's a lot of information going on here. Essentially, we're going to be pushing a box across a rough surface, and we want to determine a value that we call the coefficient of kinetic friction, which is really a measurement of the roughness of our surface that we're moving on. So we're going to draw a picture here first of what's going on. Okay? So we've got here some ground, and we've got a box, right, full of supplies, and I'm going to be, draw myself in red here, I'm going to be pushing on the box. Okay, just a very rough picture. Okay, this is not a free body diagram, so again, do not worry about the arrow pointing toward the object. We're just generally showing a picture here. Okay, we're going to be pushing on that object, and we're going to be getting the object moving, but it is moving across a rough surface, so there's some friction involved here. I'm told a few things that will be important. The mass of our object is 55 kilograms. This force here, we'll call it a force of push, right? That is a form of a contact force or a normal force, which we'll get into here in a moment. But it is a push force, and we're told that push force is equivalent to approximately 230 newtons. Okay? And we're also told that we're going at a constant velocity. That is important because if our velocity is constant, then by definition that means we have no acceleration. We are not speeding up or slowing down. We're still moving, but we're moving at a constant velocity. Okay, so we have a picture, and we've jotted down some of the numerical values that we're given. So now the next thing would be to draw a free body diagram of our box. That's the main object that we care about here. So we've got our box. Now I already drew in a push force, so I'm going to draw that over here. F, push. It is a form of a normal force because there is contact here. But we'll be a little bit more specific and call it a push force. We're told that push force is equivalent to 230 newtons. Now, as I push our object here across the rough ground, we're also told that there's some friction involved with our situation. So as I'm pushing our object, friction is a force that wants to resist any sliding. So as our box is sliding to the right, friction wants to resist that. So I'm going to draw something over here. We'll call this F sub K for kinetic friction. And I'm going to put a question mark here because we don't know what that force is. And we can assume that we're on the Earth here because we're not told we are somewhere else, which means we'll have a force of gravity acting on our object. We don't know what that is yet. We just are going to draw it in. And then our object, we have to ask, well, is there a tension force here? Does it sound like there's a rope or a string or a wire involved? And then is the object touching anything? Well, yes, by definition, it's touching the ground. We're told we're moving it across the ground, so there will be a normal force. Normal will always be perpendicular to contact, so this would be Fn. Okay, so now we have a picture of what's going on. This is kind of what the first couple of parts of the group problem are going to ask us to do. Now, the next thing is that we need to understand what we're asked for. We're asked for the coefficient of kinetic friction. That doesn't seem to show up anywhere directly, except for maybe over here with this force of kinetic friction. So we might want to focus in here on F sub k, but we don't know yet. The problem is next going to ask us to write out Newton's second law for both directions. I'm going to start with the y direction. The sum of forces in the y direction is equal to mass multiplied by acceleration in the y. And in the y direction, I have two forces in blue. Normal force going up, gravity pointed down. So we'd have Fn positive minus Fg is equal to mass times acceleration. But remember, we're told we're moving at a constant velocity. So our acceleration is 0. Mass, or any number times 0, would give us 0. That is because we have a constant velocity. So Fn minus Fg equals 0. I can then move Fg over. I can add this value to the other side of my equation. And now we have a relationship that looks like this. Our normal force is equal to our force of gravity. That won't always and forever be true, but it will be true here because our object is not accelerating vertically. It's not moving up and speeding up, and it's not moving down and speeding up, right? It's not accelerating in the y direction. Now we'll look at the x direction. So the sum of forces in the x direction is equal to our mass multiplied by acceleration in the x direction. And in the x direction, we also have two forces, our push force and our force of kinetic friction. I'm going to say the push force is positive because it's to the right, which is our typical positive convention. So Fp, or F push, minus Fk is equal to, well, again, we're told the object is moving at a constant velocity, so acceleration is 0, and anything times 0 will just give us a value of 0. So Fp minus Fk equals 0. Same approach, I can add Fk to both sides of my equation. Fk minus Fk, those cancel out. And now we have F push is equal to our force of kinetic friction. So now we have a few relationships. Now, these relationships, what we need to understand, these are not always and forever going to be true and consistent. They're only true and consistent in this scenario given these parameters. Specifically, that we have a constant velocity or no acceleration. Do not always assume normal force equals your force of gravity, or pushing on an object will always equal the force of kinetic friction against that object. These are only true given the parameters that we have. Now, this is a very good start on our problem. The issue can be, I still don't see the variable that we're looking for. The problem wants us to find our coefficient of kinetic friction. Now, based on what we covered in class, we talked a little bit about this. We have an equation for our force of friction that looks like this. Our force of friction is equal to our coefficient of friction multiplied by the normal force. So this is where our coefficient shows up. So in order to find that coefficient, I need to know what is my F sub k and what is my F sub n. Okay, now that I'm here, I need to find these two things, Fk and Fn. Now, Fk, we already determined that it's equal to F push. And we actually know what F push is. I'm going to move this down here. We know F push is 230 newtons. So that means F push equals Fk, which is equal to 230. So, X marks the spot, there we go. We know what our kinetic frictional force is here, because it's equal to our push force, because we're at a constant velocity. Now Fn, we know is equal to Fg, because of what we've done with Newton's second law in the y direction. Again, we cannot always assume those will be equal. We have an equation for force of gravity, that is the mass of our object multiplied by acceleration due to gravity. We can assume we're on the Earth here. Our mass, I believe the problem told us was 55 kilograms, and G for the Earth, 9.81 meters per second squared. So we'll take 55 multiplied by 9.81, and we get approximately 540 newtons. It's about 539.5. Not exactly what we want. There we go. So Fg is equal to, we'll go 539.5 39.6 newtons. And because of the relationship we determined from Newton's second law in the y direction, that is equal to Fn. Okay, so now we know Fn, we know Fk, which gives us enough information to solve for our coefficient. So Fk is 230 newtons, is equal to our coefficient, what we call mu sub k, is equal to our normal force, which we determined to be 539.6 newtons. So now to get mu sub k by itself, we'll divide by 539.6 on both sides of our equation. Again, whenever we do to one side, we always have to apply on both. So 539.6 over 539.6, those cancel out. And now we have an expression, mu sub k is equal to 230 newtons divided by 539.6 newtons, and we get a value of approximately 0.426. Now, as we'll talk about in class, the coefficient of kinetic friction does not have a unit. It's one of the very few variables we will deal with that is what we call unitless. It's really a measurement of the roughness between two different surfaces, and there's not a quantifiable unit that we have. Okay? As we talked about in class, this is an appropriate value for a coefficient of kinetic friction. Usually they're somewhere in the ballpark of about 0.2 to about 1.5 or 1, depending on how smooth or rough our surface is. But what I want us to understand, the takeaway from this, is how we solved our problem. And we need to go back to the process that we talk about in class. Drawing a picture, creating a free body diagram based on the forces that we know are acting, applying Newton's second law. Those three steps will be true of any process that we go through to analyze the forces on an object. Draw a picture, create a free body diagram, apply Newton's second law. We will use those processes all throughout this year, and it's important that we understand how to get to our answers based on those steps. So, hopefully this gets you going, working through group problem 4A, especially if you missed this in class. If you do have any questions, do not hesitate to ask. So we can see our value. Good luck.